Hello students, welcome to another session of All Force e-learning program. Right now in this session, this is session number 59. Right, in this session we will talk about the concept of electrical potential energy. The electrical potential energy of the system of charges or electrical potential of a charged body or for various things. We will discuss about this. But before going to this, let's have a recall of what are the necessary concepts to understand this topic, right? So I was telling you electric potential is the state of electrical state of the body, right? It determines the direction of flow of charge. Electric potential is defined as the amount of work done. Electric potential V, it is the amount of work done per unit charge. The work done in moving a unit positive charge from infinity to the point in the field. Electric potential, right? Then potential difference we have learned. This is the work done in moving a unit positive charge from one point to another point in the field, from one point to another point. This is electrical potential difference in the field there. Later we have derived the formula for electric potential due to a point charge 1 by 4 epsilon Q by R. Potential due to multiple charges, algebraic sum of all the potentials, right? We have derived the potential due to various charged bodies, so on and so forth. And the potential V can be defined as minus integral E dot dr. Well, using all these things, let us now understand what is electric potential energy. Now, first of all, potential energy. You know, the term potential energy is confined, is linked to conservative forces. Whenever there is a conservative force against whom you do work, against a conservative force, if an external agent is doing work, in doing work it spends energy. Now the energy spent is stored in the system as potential energy. Potential energy is a term linked to conservative forces, gravitational force, elastic force, and you know, even electric force is a conservative force. So even with respect to electrical force, there is potential energy linked to it, right? So it is actually the energy of the system when external work is done in moving the charges, displacing the charges, right? Now potential energy in this confined to electrical field is of two types. It is the electrical potential energy, energy of interaction between the charged bodies, or it is the energy of interaction between the charged particles, or it is the self potential energy of a charged body. So we can study, we can understand the potential energy, electrical potential energy for two different cases. The interaction energy between the charged particles, or it is the self energy of a charged body, right? Now potential energy, actually I was explaining when we were talking about potential, right? So I defined electric potential V as the amount of work done in moving a unit positive charge from infinity to the point in the field. I was moving the charge from infinity to the point in the field, right? In moving the charge point charge, the external agent was doing work, spending energy. In doing work, the energy spent. Now the energy spent is stored in the field in the form of potential energy. Let us consider, for example, imagine that there is an external field like this. There is an electric field existing in a space. There is an electric field E. Now you know, in the electric field at different points, the potential is different. Potential varies from point to point there. Now I am moving a charge. A charge is moved from infinity to the point in the field. In moving the charge from infinity to point, there is work done. The work done by the external agent in moving the charge from infinity to the point. Let's suppose at a point the potential is V. The potential is V. At a point P, here suppose in the electric field. Then I am moving a charge Q from infinity to the point in the field. You know, according to the definition of electric potential, it is the amount of work done in moving the charge, W by Q. So cross multiplying, the work done is V into Q. So the work done by the external agent in moving the charge, W work done is, now this work done is stored in the system as potential energy U. So potential energy is VQ. The energy of the system, the energy that is stored in the field, the energy that is stored, electrical potential energy is V into Q. Well, it is for different points the potential differs, then the potential energy also differs. For a particular point at a distance r, U at that point at a distance r, it is V at that r into Q. So this way we define electrical potential energy. It is the work done, actually electrical potential energy is the work done by the external agent, or it is the negative of the work done by the field, the negative of the work done by the field actually. So therefore potential energy is the potential energy work done against the field minus W, right? So well, work done is potential per potential into charge. So it is potential is V, potential energy, it is the potential, final potential at the final point minus potential at the initial point into Q. Vf minus Vi into Q. So this way you define the potential energy of the system there, right? So potential energy is a term linked to conservative forces, conservative fields, right? Like gravitational force, even electrical force is a conservative force. So for this conservative force there exists a term called potential. So it is actually defined, it is the energy of interaction between the field and the charge, right? So therefore the work done in moving the charge from infinity to the point in the field, this work done by the external agent is stored in the form of potential energy. So this way we define potential energy. From this we can derive a unit, the unit of energy, unit potential difference is measured in volts, and we know the charge is measured in coulombs. So volt into coulomb is joule. Well, 1 volt into 1 coulomb is 1 joule. Now from this we can derive a small unit called electron volt. 1 electron volt, 1 electron volt is 1 electron into 1 volt, and 1 electron is 1.6 into 10 power minus 19 coulombs, these many coulombs into volts. But coulomb into volt is joule, so it is 1.6 into 10 power minus 19 joules. So this way the unit of energy is, electron volt is not a unit of potential, it's not volts, it's neither the unit of charge nor unit of potential, it is the unit of energy. In fact, the smallest unit of energy, 1 electron volt, it is 1.6 into 10 power minus 19 coulombs, very small, 10 power minus 19. The energy, this is actually the energy required to move an electron through a potential difference of 1 volt, to move it from low potential to high potential through a distance of work done in moving electron through a potential difference of 1 volt is 1 electron volt. So 1 electron 1.6 in 10 power minus 19 joules, right? So this way we define potential energy. It is the energy confined to the field there. It is stored in the field. Energy is stored in the field, not in the bodies. It is stored in the field. So the energy that is stored, or the energy stored due to the work done by the external agent, that energy is work done in moving a charge from the infinity to the sorry W is VQ. So energy, this work that is stored as energy, it is V into Q. With respect to that point, at a distance r, it's V of r into Q. For this way we find out the electric potential, right? Thank you. Yes, now we shall find out the electric potential energy of a single charge. Single charge is an external electric field. Suppose there is an external electric field, in which the charge is moved from point A to point P. The charge moved from point A to point P. Now, according to the definition of potential, it is the work done in moving the charge from infinity to the point in the field. So at these 2 points, let the potential at A be VA and the potential at B be VB. Now I am moving the charge from right A to B, right, in this field A to B. Whatever work done in moving the charge, right? So according to the definition of electric potential, potential difference, it is the amount of work done in moving a unit positive charge from low potential point to high potential point, or from one point to another point in the electric field. So suppose the electric field is E, like this, a strong electric field. I am moving the charge from A to B. I am moving the charge from A, low potential point, to high potential point against the field. Then we know the work done in moving the charge from A to B, it is the negative of the potential energy minus AB. So it's Q times potential at B. Actually this is, it's minus of Q of VA minus VB. Well, multiplying minus, I get Q of VB minus VA. So it's Q of the potential difference. So the work done in moving a charge from low potential to high potential against the field, in doing work you spend energy. The energy spent is stored in the form of potential energy. So the potential energy of a single charge in the electric field, it is charge times the potential difference between these 2 points. If the potential difference between these 2 points is delta V and the charge moved is Q, then the work done in moving the charge W, work done by the external, now this is stored as potential energy delta U. This is the potential energy. Well, work done by the external this thing, it is final potential energy minus initial potential energy. So U final minus U initial. But work done by the field is W. It is initial minus final. It is the negative of the work done by the external. So it is U initial minus U final. So therefore du, change in potential energy, is minus of the work done against the field. So it is work done by the external field. Is it? So therefore potential difference is work done in moving it from initial point to final point by Q naught. So final potential energy minus initial potential energy by Q naught. You know, potential energy or work done. Now we know work done is minus integral F dot dr. F dot dr in moving it from initial point to the final point by Q naught. But you know, according to the definition of electric field intensity, we know E is equal to F by Q naught. So therefore E is F by Q naught. So F by Q naught is E. So it's minus initial point to final point E dot dr. So this way we define the potential energy of a single charge in an external electric field E. If this is an electric field E moving through a displacement dr, then the potential difference is this. Now the potential energy in moving this, right, work done, this is into Q. So it's minus Q times R1 to RF EI E dot dr. Well, this is the potential difference. Its potential difference is minus of this. So potential energy is potential difference VF minus VI into Q. This is the potential energy that is stored in moving the charge from the initial point to the final point. This way you derive the potential energy for a single charge, for one particular charge in an external electric field. So if I imagine a charge Q in an external electric field E, I am moving the charge from point A to point B, initial point to final point. Then the work done in moving from A to B, it is the minus of the potential energy that is existing between A and B. So it's Q times, it's minus Q times potential energy is VA minus VB. Right, Q into VA minus VB, multiplying minus, I get Q into VB minus VA. So Q into delta V. Right, so that way we derive the formula for the potential. Right, thank you. Now potential energy due to the system of two charges then, right? Imagine there are two charges Q1 and Q2 separated by a distance R. Two charges Q1 and Q2 separated by distance R. Let's suppose the charges are positive, Q1 and Q2 like this. At a distance r. This is at point A and this is at point B. Now I was telling you, electrical potential energy can be defined for a single charge in the electric field. Potential energy due to interaction between the charged particles, and it is also the self energy of a charged body. So you can define the potential energy. So let us take it for charged particles. Let's suppose there are two charged particles Q1 and Q2, right, at point A and B. In fact, with respect to the Cartesian system, this is at a radius vector r1 bar, this is at radius vector r2 bar and rab bar, so it is r bar. Now if we have to find out the potential energy of the system of two charged particles like this. Now for this, first let us imagine this charge Q1 be existing at point A. So initially charge Q2 is not existing. There is charge Q1 existing at point A. Now when the charge is at point A, at a distance r from it, potential due to the first charge at a point B due to the charge Q1. But this charge is not existing, suppose, initially. So the potential due to A at that point B is 1 by 4 pi epsilon naught charge at A, that is Q1 by R. Q1 by R. Now the potential at B is V1, that is 1 by 4 epsilon Q1 by R. Now in the electric field of A, I am getting a charge B from infinity to the point B, charge Q2. So the work done in moving a charge from infinity to this point is, now the work done is, I am moving a charge Q2 from infinity to this point. The work done is potential at that point into charge Q2. We have just now derived the work done in moving a charge to a point P. It is potential into Q. So work done W is VQ. So therefore, the work done in moving a charge from infinity to the point of the field, W is V. Potential at this point, V1 into Q2. So the work done is V1, 1 by 4 pi epsilon naught Q1 by R into Q2. And you know, this work done is stored between them in the electric field as potential energy. The external work done is stored in the system as potential energy. Now this is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. This is the work. The work done is 1 by 4 pi epsilon Q1 Q2 by R. This is the work done. You can even do the same thing by considering the other way also. Let initially there is no charge A. Initially charge B is charge Q2 is exiting at point B, right? Initially there is no A, no charge Q1. So due to this charge at B, the potential at A due to charge B, that is charge due to Q2, potential at A Q2, V2 is 1 by 4 pi epsilon naught Q2 by distance of the point R. We have derived the formula for the potential due to a point charge. V is 1 by 4 epsilon Q by R. So potential due to charge at B at A. So it's 1 by 4 epsilon Q2 by R. Now charge Q1 is brought from infinity to this point. In getting the charge Q1 from infinity to this point, the work done in moving the charge from infinity to this point W. Now this work done is potential at that point V2 into the charge that is being brought Q1. So potential here is V2. I am getting a charge Q1 from infinity to this point. So therefore the work done is equal to 1 by 4 pi epsilon naught. V2 is Q2 by R into Q1. So the work done is 1 by 4 pi epsilon naught Q1 Q2 by R. Now this is the work done. Again the work done is stored as potential energy. It is the same thing. So whether you consider the field of the first, get the second, or consider the field of second, get the first, the interaction energy is same. So the interaction energy between the charged particles is independent of the location of the points. Whether these 2 points are here or here, it only depends upon the distance between them. It does not depend upon the location. It is even independent of the path followed in moving the charges. Work done is independent of the path. Electric field is a conservative field. In a conservative field, work does not depend on the path. Whether you move the charge from here to here directly or the path like this, or whichever way you move, in the work done is same. Work done does not depend upon the path followed, it only depends upon the displacement between them. Is it? It is a conservative field. So the potential energy between two charged particles is defined as 1 by 4 epsilon q1 q2 by r. Whether we consider first field of the first charge, in that field the second charge is brought, or we consider the field of the second charge in which the first charge is brought, the potential energy is same. Now the potential energy of the system depends on the product of the charges q1 q2, and it is inversely proportional to the distance between them. So potential energy depends on the distance between them, not on their particular location, at what points they are existing. It's a scalar, it has no direction, right? So it depends upon the product of the charges and the distance between them. So this way the electrical potential energy between two charges can be defined. Now this potential energy can be positive, can be negative, or it is even zero. Positive, suppose Q1 is positive and Q2 is also positive. So when Q1 is existing, I am getting Q2. So I am moving positive charge against another positive charge which repels this. So the external agent has to do work in getting the charge. In doing so, the external agent does work, spends energy. Now the energy is increased. Energy of the charge system increases, positive. Had Q1 been positive and Q2 negative, now negative charge is attracted to the positive charge. Then negative charge Q2 moving from infinity to point is the work done by external agent is negative. The potential energy is negative. In fact, the potential energy of the system decreases. It is negative. So when the charge Q2 is at infinity, the potential energy is zero, no interaction. Now while moving from infinity to here, the negative charge, then positive charge attracts negative charge. It comes rushing towards it. Kinetic energy increases, potential energy decreases. Negative it is. When these two charges are at infinity, the potential, no interaction, potential energy is zero. So potential energy of any system can be positive, negative, or it can be zero. Suppose if two positively charged particles like this, Q1, Q2, if they are moved closer, if I am moving them closer, the distance between them is decreased. In decreasing the distance between them, the external agent has to do work. In doing work, spend energy. Now that energy is stored in the system. So potential in the system increases. Potential in the system increases. If two protons are moved towards one another, then potential energy increases. Even if it is minus and minus also. Two electrons, let's suppose, two electrons are at a particular distance. I am moving them closer. Negative, minus. Even though it is minus, negative into negative, the answer becomes positive. If they are moved closer, then two electrons moving closer towards one another. So when you are moving closer towards one another, there is force of repulsion between them. Against him, you have to do work. In doing work, you spend energy. The external agent has to spend energy. The energy is now stored in it. The energy, potential energy of the system increases. Potential energy of the system increases. Instead, if there is a proton and an electron, they are moving towards one another. Proton electron attracts. There is attraction. So when the electron moves towards the proton, it is attracted towards it. It is accelerated. Kinetic energy increases. Potential energy decreases. So when the like charges are moved closer, towards one another, potential energy increases. If they are moved away, like charges are moved away like this, then they are moving apart. In moving apart like this, potential energy decreases. Similarly, if unlike charges, if I consider unlike charges moving towards one another, when unlike charges move towards one another, they accelerate. Their kinetic energy increases, potential energy decreases. When they are moving away, now when in moving the unlike charges away, plus and minus, actually there exists an attraction force. Against the attraction force you have to move. The external agent has to do work. Potential energy increases. So this way, the interaction energy between the charged particles depends upon the product of the charges and the distance between them. It can be positive, negative, zero, right? It is independent of the distance between them. The path followed, it is independent of the path followed. Suppose if there are two charges like this, there is a charge Q, capital Q. I am moving in another charge I am moving a charge from here to here. Another charge Q from here to here, from this point to this point. There is no change in potential energy because the distance here and the distance here is same. The potential energy initial and potential energy final same. The change in potential energy is zero. So that way, the potential energy of the system depends upon the distance and the product of the charge particles interacting, but it is independent of the location, independent of the path followed. It does not depend upon those things, right? Thank you. कितने मिनट हुआ?
25.
पूरा मिला के
25.
25